Welcome back. Good afternoon again. My name is Mike Dake. I'm Senior Vice President of Health Sciences at University of Arizona, and I'm pleased to be able to introduce our third research showcase dealing with some of the challenges we face globally in health today. We're going to be tagging on to our last session with another climate-related issue and stressor. And our final third session is entitled Safeguarding Health from Climate-Related Stress in Arid Lands. You're going to hear from a talented group of researchers that are leading efforts to further study Arizona's unique environment and the health effects on the people who live there. They're looking to apply the lessons they've learned on a global scale to build health resilience in individuals, individual communities, and nations around the world. The moderator of this afternoon's session is Dr. Frank von Hippel. Dr. von Hippel is a professor of environmental health sciences in the Meladina Zuckerman College of Public Health and the lead of the One Health Research Initiative at the University of Arizona. His work uses local wildlife and laboratory animals as models for human exposure and disease, and we're honored to have him guide us through this final session. Please welcome Dr. von Hippel.
Thank you so much, Mike, and I really appreciate the emphasis in health sciences on issues to do with climate change facing these global threats that we're all concerned about. Climate change is one of those and a very important one. It's also great to have our colleagues here from really around the world, colleagues from France, colleagues from Arizona, from the DC area, from agencies. So really happy that everyone is here and that we can hopefully work together to really solve some of these global threats that we're facing. So this is just our agenda for this next part of our session. I'll start out discussing a little bit about One Health, climate change, and arid environments, introducing this area. Then Professor Nathan Charrington will talk about research centers and institutes and related issues at the University of Arizona and how that relates to this initiative that we're pushing in climate change and pollution. Then Professor Mark Verhoekstreet will talk about safeguarding health from climate-related stress in Arizona and show a model that we're developing around how to approach these problems in an integrated fashion. And then Dr. Sylvette Tormente will talk about Arizona as a model for global initiatives addressing climate change and health and really bringing in our collaborators from France through CNRS. So what I'd like to do is just give a little bit of an introduction to set the stage for all of this. And to do this, I wanted to introduce the concept of planetary boundary threats. So we focus a lot on climate change, and rightfully so, but it's one of only 9 of these known planetary boundary threats, global scale issues that are threatening the sustainability of life on Earth, including for people. This initiative we'll talk about today. It's a collaborative effort between the University of Arizona, Arizona State University, and the French National Center for Scientific Research, or CNRS, along with this subsidiary in Arizona, the France-Arizona Institute for Global Grand Challenges. And what we're addressing in this initiative, of course, involves climate change, but not just climate change. We're also addressing the planetary boundary threat that's known as novel entities, which are the 350,000 or more synthetically produced pollutant chemicals that are out in the environment, along with other kinds of pollutants such as radionuclides. And this effort also integrates issues with biosphere integrity, biodiversity loss, land system change, as you also saw with the last session, and also freshwater use. So there's really 5 of these planetary boundary threats that are incorporated into this initiative we would like to pursue in climate change and pollution in arid lands. So why arid lands? 2.1 billion people on Earth live in arid lands. And of course, the Earth is becoming ever more land that's encompassed with arid lands. But not only that, the population growth rate in arid lands is the fastest of any ecological zone on Earth at about 18.5%. So growing pressures, really rapidly growing pressures in a part of the world that's already naturally stressed and becoming even more so. And once we get into arid lands, there's a lot of different things that we have to and want to consider, including wetlands and arid lands. They are of paramount importance. Something like 90% of the productivity in desert environments occurs in the riparian zones, the zones around where the water is. And of course, we have shared water resources in a changing climate. Arizona and neighboring states have been in headline news around the world for this, as the reservoirs have been drying out, and we have major dams that are just barely functional, and major water resources, Lake Powell, Lake Mead, that are barely functional. So how do we have these shared water resources in a changing climate, and what are the air and water quality issues that we get in a changing climate, which is really what we want to introduce today. So we have this model that Mark will talk more about technology, surveillance, health effects, health interventions, preparedness, and resiliency, and wrapping all of these together. But just to introduce the concept of why are we concerned about pollution as it relates to climate change in arid lands, I think the Great Salt Lake is really an excellent warning of why we need to worry about this. You can see the retraction of water in the Great Salt Lake through overuse in the watershed as well as drought conditions. And what this means is that you now have former lake bed that's been covered by water for who knows how many millions of years. And now those sediments are available for erosion, and they include lots of toxic metals and metalloids. The air quality around Salt Lake is in really dire condition, as you have toxic metals that are now an important part of the landscape, and the conditions only getting worse. And then if you look at the water itself, maybe Great Salt Lake isn't the best example of this as a saline environment, but in normal freshwater environments where you have reduction of the water, that means the pollution that's in there is going to be even more concentrated than it was before, which makes the water even less available for uses you may have, from drinking water to irrigation water to water resources for wildlife. So that's the water issue. As water level goes down, water and air pollution go up. And so we have a growing population. At the same time, we have aridification due to climate change, and we have increasing air pollution. These are some photos from Phoenix of some of the issues with air pollution around there. And these, of course, you have natural events like dust storms, but as with greater aridity, these are going to become even more prominent than they were in the past. And these can include not just dust particles, but toxic chemicals. They can include pathogenic microbes like pathogenic fungi. And so it's really this mixture of pathogens and contaminants that we're concerned about with regard to air pollution. And the same is true for water pollution. So this is just an example from the Arizona Department of Environmental Quality showing arsenic concentrations around the state. Arsenic is naturally occurring in Arizona. It's also been used historically in agrochemicals and other uses in industry. And we have quite a lot of problems with arsenic pollution around Arizona, as do many other parts of the world. And so it's a carcinogenic metalloid, it's associated with kidney disease, all kinds of other things. So we have this growing population, aridification, and water pollution. Now we're talking about not just chemical pollutants, naturally occurring metals and metalloids, pesticides, all of the kinds of things out there, but also salinity. So as the water level goes down, salinity goes up, the water becomes even less usable, the demands become even more difficult. And we also have increased concentration and problems with pathogens in our water. Things like Mark will talk about with pathogenic microbes, viruses, bacteria, and so on. So we have climate change and arid lands, and one of the things that we can bring to the table in Arizona is perhaps the two premier universities in the world that are in hot desert environments are in Arizona, the University of Arizona and Arizona State University. With all the resources that we have, all the experience working in arid landscapes. In addition to these issues, resources with Arizona, we also are on the border, and there are a lot of issues with border health. Climate change is also exacerbating migration crises, and this brings up a lot of public health issues that we're right there at the front lines of and have a lot of people working on. In addition, as you've already heard, agriculture is important, and it's very important in Arizona as well. So I've circled Yuma here. The Yuma region on the border with California and Mexico produces 90% of the winter lettuce crop for North America and many other crops. But this also is associated with intensive pesticide use. It's industrial level agriculture. There's pesticide applications happening year round, 234 different pesticides in common use in this county. So there's a lot of issues with that. A quarter of those pesticides in use are considered hazardous. That means carcinogenic or developmental disruptors. And these, of course, are affecting people and wildlife. So we have a number of model communities that we are kind of developing as ways to push forward on this initiative on climate change and pollution. Mark will talk about 3 of these today. I'll just mention a little bit more about the Yuma border community because I've been doing a lot of work down in Yuma since 2016, and this involves serious water use issues. This is Colorado River groundwater and surface water that's producing these crops. We're growing cotton in the desert, all kinds of other crops, date farms, and of course citrus, and of course leafy green vegetables. And so this research that we've been doing in partnership with various institutions in Yuma County has been funded primarily by the Flynn Foundation. We've been working with the Regional Center for Border Health, which is the health providers primarily for farm workers and their family. The labor here is migrant and seasonal farm workers, mostly from Mexico. We've been working with Yuma Regional Medical Center, which is the primary healthcare provider in the city of Yuma, with Campesinos Sin Fronteras, which is the advocacy group for the farm workers working on both sides of the borders, and also with the Cocopah tribe on looking at some of these issues for a small tribal community that sits on the border and has Cocopah members on both sides of the border. So really an opportunity to work on water pollution, air pollution issues, and as they relate to increasing aridification, intensive industrial agriculture, tribal communities, international communities, and all the rest. I'm in the One Health space, so all of my research I do on pollution involves the use of animals, typically wildlife, that we find that either looking at the impacts of pollution on wildlife itself in tandem with humans or as a model for human health. So just as an example, with this Yuma project, we use the cactus mouse, Paramyscus eremicus, you can see here. And in the mouse, we're able to collect them from the same places where people are exposed. We're able to measure the contaminants in the mouse, do the contaminant chemistry. In this particular project, we take out the brains from the mice from areas of intensive pesticide use versus reference areas versus landfills and so on. And we're able to do the gene expression, the transcriptomics and metabolomics in the brains and look at what can we infer about children's cognitive development by looking at a mouse in the same environment. There's a lot of concerns about how these agrochemicals are affecting children's neurological development, including things like various behavioral outcomes in children. But we can also look at things like thyroid disease, reproductive disorders in the mouse using histopathology, and then at the same time do the similar kinds of measurements in people, including in children, because we can look at hair, we can look at fingernails, and we can do the same urine, and we can do the same kinds of contaminant chemistry to understand human exposures and then look at associated health effects in people. Part of the reason we're doing all this is also to develop health interventions, because we shouldn't just study to find out what the problem is. We need to solve the problem. And we're doing this in a variety of ways. I just put up one cute example here, which is we worked with a University of Arizona art class, and all the students in the class they wrote comic books, photonovellas, where we provided the script, and it's to educate farm workers about pesticide exposures to reduce their levels of exposure. And we got 20-some wonderful comic books that we're now providing to the farm worker communities to help educate them on exposures to pesticides. So Arizona has 22 federally recognized tribes. It's also bordering 5 other U.S. states, and we have the international border. And this provides tremendous opportunities for collaborative research as well as improved management of shared resources. So just going from south around counterclockwise, Mexico, New Mexico, Colorado, Utah, Nevada, and California. Of course, these are all involved in negotiations over the use of Colorado River water. But also, we're working on a lot of initiatives working with the northern Mexican border states and the southern U.S. border states on health, including climate change and health. So part of what we want to do is to be able to integrate data that's going from ground-based sensors all the way up to remote sense data. Here's just an example that from NASA of looking at shallow groundwater drought indicator. This is a snapshot from June 20th, 2022 at the height of the drought for that year. And you can see that Arizona is in serious drought conditions at that moment in time, as we have been for much of the last couple of decades. And here, just zooming in on Arizona and using another data set looking at the drought response index in plants, you can see that, again, Arizona's been facing serious drought conditions with a lot of repercussions across the state. So how do we best integrate data going from field-based monitoring sensor technologies all the way up to remote sensing, probably using AI approaches to handle the immense amounts of data that we're talking about with this kind of integration. So I just want to mention some of the centers and programs that are relevant to all this at the University of Arizona. So we have the Arizona Institute for Resilience that includes 15 centers and programs that are designed to develop and apply diverse knowledge to create solutions to environmental change. And these include the Climate Assessment for the Southwest, which is improving the ability of the region's social and ecological systems to respond to and thrive in a variable and changing climate. The Indigenous Resilience Center, which is working to help make communities thrive and adaptable as facing environmental and societal challenges. The Center for Climate Adaptation, Science, and Solutions, which helps to develop and link research-based knowledge with decision-making. We have a new NIH-funded P20 planning grant called SCORCH, which is meant to improve health equity in arid lands across the lifespan. We have the Southwest Environmental Health Sciences Center, whose mission is to facilitate and implement innovative research aimed at understanding the mechanisms underlying environmental health science risks and disease among people living in arid environments and experiencing climate change. We have the One Health Research Initiative that I lead that's funded by the state of Arizona, and this is working with programs all across campus to facilitate One Health research and find solutions to these kind of global level as well as local level problems that we're all facing. And then we're working closely with Arizona State University, which has sustainability research initiatives, including the Biodesign Center for Environmental Health Engineering, the Human Health Observatory, the ASU Banner Neurodegenerative Disease Research Center, the Urban Climate Research Center, and the Decision Center for Desert Cities. So for the next two presentations, we're going to hear about the air side and the water side of what we're trying to do with this initiative. And when we say pollution, we're not just talking about chemical pollutants, we're also talking about pathogenic microbes as part of that. So keep that in mind. We're going to start with looking at climate change and air pollution, and then we'll look at climate change and water solution within this framework of preparedness, resiliency, surveillance, health, interventions, and continual improvement working around that circle. So Arizona presents incredible opportunities to be at the forefront of international research on climate change and health in arid lands. And we're eager to integrate our resources, acquire new resources, build collaborations, and create big data approaches to combat climate change and pollution in this context. With that, I would love to introduce our next speaker, Dr. Nathan Charrington. Nathan is Associate Dean for Research and Graduate Studies in the College of Pharmacy. He's also the director of the NIH-funded Southwest Center for Environmental Health Sciences. He's the interim director of the Arizona Board of Regents Center for Toxicology, and he's a recipient of the Achievement Award by the Society of Toxicology and a fellow of the Academy of Toxicological Sciences. Thank you very much.
So I just want to pause briefly. In my office, I have two pictures. One of them is my grandfather, who is at the White House shaking hands with Lyndon Johnson. The other one is the press release from Rutgers University talking about Dr. Daines's research that led to the signing of the Clean Air Act that he went to go. And so I'm almost there, Grandpa. Close. But air pollution is a family thing for us, and so it's a great opportunity to be here. Thank you very much. Tomorrow I have to leave early. I'm going to the NIH and IEHS Center Directors meeting in Houston to talk about climate change. And just for some contrast, I will wait patiently as they discuss sort of the East Coast model, and it's appropriate to do so. So they'll talk about hurricanes and tornadoes and flooding and rising sea levels, and I will wait patiently until they start talking about arid lands and droughts and things like that. Then we will talk about the resource opportunities that we have in the desert Southwest. The heat wave that we had, it was sort of, it was highlighted by a New York Times. It was sort of started, the emphasis on the heat wave and the impacts there was started with a New York Times article that recognized heat as a significant stress. So the sort of East Coast approach to climate response and disaster relief is appropriate for much of the United States. But FEMA has never declared a disaster for heat because of the legislation. It's limited, that they can't do it for heat, even though heat has resulted in more deaths than any other climate-related disaster, all of them combined. And so heat and the resulting the stress on the water resources, and then that becomes air pollution, is highlighted by. So this was a Science Magazine cover piece last month. And so there are lots of physiological outcomes of heat stress, and those are pretty well documented. So each of these are R01 level research initiatives at the University of Arizona. And so we don't just represent the three people who are going to be speaking to you, but we represent literally hundreds of researchers. In my own, it's 54 different faculty members with $60 million of research on environmental health issues of climate change and the people who live there. We care about the climates, but we care more about the people who live in those climates. And so cardiovascular and respiratory stresses are well documented, and renal dysfunction, the decrease in glomerular filtration rates. These are well documented, but the thing that I want to highlight today is just an example of some of the new research that has not yet been picked up, but has significant implications to human health. And that is the idea of the basic ground rules of toxicity. So from a lay perspective, you think of the defenses that we have against things from the climate, the environment that are coming into our bodies. We have defense mechanisms. It's the same defense mechanisms that make it so that you have to take a Tylenol every 4 to 6 hours. We metabolize things and we get rid of them at a constant rate. Well, it's not constant. We can defend ourselves against toxicants very nicely, unless we have stress. So here's what happens. So this is a liver, which does most of the metabolism and elimination in our bodies. So when these environmental toxicants get in, they come to the liver, and they are moved around by these things called transporters and enzymes. And so we have multiple enzymes in our livers so that, okay, this took me forever, so watch this. This is important. So here comes the toxicant. Ready? Here it goes. They get metabolized and they get eliminated and they get taken out of our bodies. Was it worth it? I'm not sure. But under stress, so this is the new part that hasn't been picked up by the New York Times yet. Under stress, we have changes. It's called phenoconversion. We look different than we were when we were healthy. And so as a result, the transporters and enzymes are altered so that our capacity to defend ourselves is decreased. So now when we have the exact same exposures to environmental toxicants, they aren't able to be defended as easily, and in fact they stay in our blood longer than they should. And so even though the Should we call it dose? It's not the right. So the exposure of the chemicals to our bodies can be the same, but because the chemicals stay in someone under stress longer, their actual exposure is much greater than another person whose body isn't under stress. And so when we think about what is the thing that determines the toxicity in one person versus another, the inter-individual variability in response, we oftentimes think of genetics. And so here's an example of a normal person that's able to put the compound out of their bodies. But if you look down at the bottom, there's a polymorphism. And so when a person has a messed up gene, they can't do some function. And so in this case, that person can't put that compound out of their bodies. Well, that's genetics. But if you look at stress, you get a very similar response. So this is the same person. When they're healthy, they can put it out of their bodies. A nice curve. But when that person is under stress, that's the same person. They can't put it out as easily, and they almost look as bad as the genetic polymorphism patient. And so what that leads to is a measure of exposure. So what that means is that in January, when you're outside spraying your weeds or working in the farm or doing something, and you get exposed to something, if you do it in January, you have a normal exposure. When you do it in July and your body's under stress, you're going to have a twofold greater exposure, even though you got the same amount of chemical. Okay? So that process of phenoconversion is the subject of multiple research initiatives across multiple centers at the University of Arizona and others. So the first one, chronic heat stress on farm workers. So these are good, hardworking taxpayers. It's farm workers, it's landscape engineers, it's construction workers, it's road workers. These are good, solid people doing work, and they're suffering for it. So these agricultural chemicals have significant toxicities. Are you at greater risk of toxicity during the heat of the summer than you are during the winter? And does that have an effect on your health? That's done by several people at the Southwest Environment Health Sciences Center with an ongoing collaboration with Solène Marie at the CNRS at the University of Paris-Saclay. Did I say that correctly? That was great. Good. Yeah, Okay, the only thing worse than standing out in the middle of the summer working in the yard is doing that with a full set of firefighter gear on. And so having a huge coat on and 114 degrees, that's going to be worse. But when they're done, they go back into the air conditioning. And so the chronic stress of heat, a lot of the farm workers, they are out in the heat all day, and then they go home and they don't have air conditioning. Okay? What about the firefighters? They go out and they're in intense heat, and so they're exposed to very unique chemicals. And so they have increased risk of several cancers, reproduction, and even in the milk that female firefighters give to the babies, they have chemicals that are coming from the fires, and do those change over time with stress. And then also pregnancy. Mothers and children have outcomes that are influenced by the stress of heat, and the exposures that we have are magnified because of heat stress. And so that's done with, I forgot to say that we have the largest Center for Firefighter Health and Research Collaborative than anywhere in the United States. And the new funding for the SCORCH, the P20 planning, as well as the One Health system, there are several faculty in each of these research endeavors that are looking at this unique increase of climate change and heat and their outcomes on human health and in lots of different people. And so how that relates to the integration that we'll talk about, and so I just tried to provide the health outcomes, and Dr. Hoogstraat will continue to work the air and now the water into that vertical integration. Back to, okay, when you did something wrong, then no, I'm just.
Thank you so much, Nathan. So it's my pleasure to introduce Mark Verhoogstreet as our next speaker. And Mark's primary research has focused on environmental microbiology and water quality. He focuses on understanding the sources, occurrence, and transport of waterborne pathogens using fecal indicator organisms and molecular source tracking. And Mark, just so you know, we're well ahead of schedule, so feel free to take your time as you go through your presentation.
Hi, everyone. So I'm actually picking up right where Frank left off. So we're going to go through this roadmap that we developed in order to safeguard health from climate-related stress in arid lands. And so how do we do this? Our group believes that with technology incorporated at every single step, we can generate a more resilient future. And so I want to spend a couple minutes going through this. And like Frank said, we have a little bit of time, so I'll spend a few more extra minutes kind of talking about the details here. The first step for safeguarding health in arid lands is actually focused on our exposures. And as Frank alluded to earlier, this group is really focused on air and water, but we know from the previous session that also exposure pathways also include food, and soils are related to all three of those exposures. Humans are primarily exposed through contaminants through inhalation of polluted air or ingestion of contaminated water, and that's what we're going to focus on for most of today. The next step in providing climate-related stress in arid lands is to focus on surveillance. That's surveillance of environmental risk factors associated with climate change. And in this case, we're going to integrate personal and community level sensors to help us quantify the chemical, biological, and physical attributes. The reason this is the first major step is because how do we mitigate a problem if we don't know the extent of the issues? And so we want to start to get a quantified understanding of what humans are truly exposed through air and water. The next step in our roadmap going forward is to assess the health effects within specific communities that stem from exposure to air and water. So in this case, we will characterize cancers, developmental disorders, gastric, respiratory, and reproductive diseases. And in this case, we're going to incorporate artificial intelligence to start to link these multiple exposure pathways and the complex environmental risk factors associated with diseases in order to understand those non-traditional health outcomes associated with some of these exposures. The next steps is once we have a understanding of the exposure pathways, the risk factors, and the health outcomes, we want to start to understand the health interventions because as Frank indicated, we're not here just to study a problem. We want to solve issues around the world. And so we'll be able to incorporate exposures and risk factors and health outcomes and start to adapt pollution-specific interventions. We can include source remediation and protection and other behavioral adaptations, including precision medicine. And that ultimately will help us get to reducing the burden of disease in our arid lands. And finally, by integrating the surveillance and health data into infrastructure, into systems operations, and into workforce development, we can protect public health, build our workforce, and ultimately build more resilient and prepared communities throughout Arizona. Now, what I'm going through today, this is just a roadmap, but I will apply it to, later in the presentation, a very specific case study that we're using in Arizona, addressing a climate and health issue. But this can be used for multiple diseases related to climate change and health in arid regions. So our hope is that by using this roadmap and by connecting our expertise in Arizona with CNRS, we can make Arizona the model location for studying arid environmental research throughout the world. And there are endless communities, there's endless stressors, there's endless stress responses that we can address this roadmap or that we can apply this roadmap to throughout the world. But today, as Frank indicated, we're going to focus on 4 select areas in Arizona. Dr. Charrington just indicated how the extreme heat affects chemicals in the body and leads to additional kidney diseases. This has significant implications for the community of Maricopa in Arizona, who just experienced 54 consecutive days of temperatures above 110 degrees Fahrenheit. With those extreme heats, we also know this community lives right within intense agriculture communities, so they're exposed to the agrochemicals that Frank indicated earlier. But unfortunately for this community, they have the state's highest chronic kidney diseases throughout the state. And so having Dr. Charrington's specific examples and research in place is going to help us better understand why these kidney diseases are occurring in the first place. Dr. Von Hippel indicated earlier about his UMA project, where he's looking at UMA and the increased thyroid disease that's occurring there. He's looking at those exposures related to extreme temperatures, as well as exposure to agrochemicals through contaminated air and water. The other community I want to talk about at the very top of the page here is one that I'll only mention here as a potential community that we want to partner with going forward. And this is the Colorado River Indian Tribes Farm, or CRIT Farm. They are located on the banks of the Colorado River, where they use that water to grow irrigated crops. As a result of this prolonged drought and allocation of water resources being cut, they've had to fallow thousands of acres of their farmland. When we turn agriculture land from productive to a desert, that increases particulate matter. And when we couple this community with the increased particulate matter in the air, with the drought, with extreme heat, with vector-borne diseases, with flooding, we have an unknown and an unimaginable magnitude for complex health outcomes. I met with the manager of this farm earlier this summer, and he is dedicated to developing and implementing technology that protects health and agriculture environments. And so this is one of the key communities that we can work with going forward. Now, those are just 3 examples. I want to spend the rest of the presentation talking about this last example on the bottom in southern Arizona. This area is experiencing increased temperatures and extreme heat, extreme population growth. We're also experiencing very limited surface water, natural surface water availability, and a poorly regulated groundwater resource. And in this southern Arizona exists Tucson, which many of you are familiar with. So Tucson, this is a map of Tucson's population over the last century, starting with about 10,000 people, and now we're over 1 million people. So in the same time period, our average yearly low temperatures have increased 8 degrees Fahrenheit. But what is most remarkable has been our transition into a reliance on groundwater. Our reliance on groundwater has come from increased temperatures, increased human demand, and we already had an environmentally sensitive resources with our surface water. This blue line that I just projected, this is one aquifer and the depth to the top of that aquifer where our groundwater is being pumped from. This is, in one aquifer, a drop of more than 300 feet. And when we over-rely and over-pump our groundwater, the land literally sinks to fill the void. It opens up with fissures and wells run dry. This is only what we see from the future, or from the surface. So this cascading effect of increased temperatures and increased human demand leads to surface water scarcity, and that in turn results in these reliance and over-reliance on groundwater. As Frank indicated, the remaining water that is present becomes concentrated with contaminants. And in one case, in arsenic, we see that those concentrations are increasing in groundwater around the world. And arsenic, unfortunately, is just one of the contaminants that we expect to increase as a result of this cascading effect. And unfortunately, contaminated groundwater or disproportionately affects some communities more than others. And we know that to be the case in rural communities. So rural communities are at the highest risk for exposure to contaminated groundwater because of their location, that groundwater is their sole source of water. And they often consume that water without treatment. And so like Dr. Charrington indicated, we care about the climate, but we care as much or more about the people living in that environment. And so when we look at who is being exposed to contaminated groundwater, we see the demographics in the Southwest United States has high percentages of Hispanics and American Indians, and those two groups are disproportionately affected by gastric cancers as well. In fact, gastric cancer mortality and prevalence is actually decreasing for the entire United States over the last 2 decades, except for these two groups. Mortality rates for American Indians is 10% higher for gastric cancer, and this is especially so for prevalence and mortality for young Hispanic males. And you might be thinking, why are you presenting gastric cancer in a climate and health talk? Well, it's because we went through and we've identified a number of risk factors associated with gastric cancer. And they include Helicobacter pylori, which is a microorganism that causes ulcers and if left untreated, causes gastric cancers, and arsenic. These two alone can cause increasing rates of gastric cancer, as I'll show later on. But another study that recently came out showed that the highest rates of gastric cancer mortality around the world, one of the risk factors for that is climate. And that is one of the new risk factors for gastric cancer that needs to be further explored. But it begs the question, can cancer be attributed to heat and other climate-related exposures, including concentrated contaminants in water, such as arsenic? So we know that cancer is not an NIH and health endpoint when it comes to climate and health, but we believe it should be. And so I want to go through a case study now that's demonstrating why cancer needs to be highlighted as a climate risk factor for gastric cancer. And so to show you how we're doing this, I present a series of studies that are being done at the University of Arizona. Part of them are funded by Dr. Charrington Center, the Southwest Environmental Health Sciences Center, and another small pilot funding came from the Research Innovation Institute, or RII, at University of Arizona. From this case study, we're again looking in southern Arizona, and we're applying that roadmap that I presented on the first slide. So again, as a reminder, this community is experiencing extreme temperatures that are getting hotter, an increased population, decreased water availability, and the water that is there is becoming concentrated with contaminants. But unfortunately, we also have gastric cancer rates that exceed those of the national average, and Hispanics make up a significant portion of our population. And as I indicated earlier, Hispanics are one of those disproportionately affected by gastric cancers. So following that roadmap that I presented earlier, we're going to first quantify risk factors associated with gastric cancers. Then we plan to define the mechanism and quantify health outcomes of gastric cancer from multiple risk factors. And then ultimately, we want to characterize the risk based off of exposure factors and population-specific mechanism. Now, I want to reiterate, this is gastric cancer focused, but this roadmap and this approach can be used for multiple diseases related to heat and environmental health. And this is just one example we're trying to demonstrate today. So how do we even begin to connect climate with cancer? Well, the first step in this case study is to quantify risk factors associated with gastric cancer using a battery of technology-based approaches. And these are just some of the approaches we plan to use. Currently, through one of the pilot fundings, we are out collecting individual exposures for gastric cancers, and these include wearable technologies such as smartphones, smartwatches, and personal pollution monitors. We're also doing a lot of omics work to really understand a person's past exposures. We're using remote sensing and passive environmental sampling within a person's home so we can get a day-to-day assessment and a month-to-month assessment of what an individual is exposed to, primarily from the water. And as these projects scale up, we plan to expand out to look at the population exposures. So we'll be incorporating more assessment of pollution mixtures from water. We plan to do a lot of community tracing for large-scale exposure events, and ultimately use machine learning to start to pull in some of the data from the multiple agencies that are collecting, air quality and water quality, and start to really understand what a person or a community is being exposed to. And we understand that data sharing has to go in both directions. We can't just continuously gather data from our populations and our communities. So we intend to give that information back to our participants and back to our communities. And we'll do that through social media, through text messages, and through cell phone apps. Our ultimate goal for this is to harness all of this data and put this into some really nice data visualization approaches where we can identify which communities are at highest risk, run it through some forecasting models so we can identify what communities in the future may be at the highest risk, and also generate the dashboards where our individual communities and community partners can go to identify what they're being exposed to and make an informed decision of how to address that. There we go. So the next step in our project was to define quantify the health outcomes associated with multiple risk factors, and then to define the mechanism of gastric cancer from multiple risk factors. And this project, the projects are in various states of completion at this point, but we intend to incorporate all of the following pieces of technology into these projects. And we'll start with sewer surveillance. Right now, we are going one person at a time to measure gastric cancer risk factors and health outcomes. But we're likely missing people either in the household or in the community. And so we hope by applying sewage surveillance, we can understand the burden of disease on the community from a gastric cancer and risk perspective. The second approach that we plan to use are cell phones, web searches, and social media posts related to health and health outcomes. So this is similar to what Dr. Casey Ernst has done at the University of Arizona with the mosquito-borne disease surveillance apps, and also the COVID Alert app that she was a part of a team that developed. We intend to use cell phones initially in this project to do health surveys and then follow up with health reminders for screening and for treatment if we identify people who are at high risk for gastric cancers. Like all environmental health scientists, I have to say the exposome. This is a lifetime of exposures leading to health outcomes and trying to really understand this. And so we aspire to contribute to this growing body of information. This is where we will incorporate artificial intelligence to start to think about all of these complex exposures and non-traditional health endpoints, such as gastric cancers from climate-related exposures. And finally, we've got precision exposures, precision medicine, and precision risk assessment. Dr. Von Hippel indicated earlier that he's using animals as part of an exposure for environmental health. The University of Arizona is using everything from cell lines to animal models to human trials to understand this. And I'm using organoids and the study relating back to gastric cancer, and we're trying to study the mechanism of gastric cancer as it relates to exposures to multiple contaminants. So to understand this connection, we took biopsies of human stomachs. We grew them up in the lab to create mini human stomachs or gastric organoids. We exposed those gastric organoids to, in this case, multiple doses of arsenic, and then we injected them with H. pylori. Remember, those are two risk factors for gastric cancers. And what we see are these results here, where with increasing concentrations of arsenic, we see increased adverse health outcomes associated with the gastric organoids. The line on the left here, these are the concentrations of arsenic, and we have the S. Lewis X antigen, which is an attachment point for H. pylori. I want you to focus on the middle column. This is the CD44V9. This is a genetic marker for gastric cancers. So you can see with increasing doses of arsenic, we're seeing increased adverse health outcomes, including gastric cancers. So these results start to suggest that that arsenic being concentrated in groundwater or in drinking water could potentially lead to gastric cancers. And so once we have an understanding of the exposures, the disease mechanisms, and the burden of disease within the communities, we can start to have a discussion about, are they overlapping? Do they come to the same or similar conclusion? And if they do, we can start to incorporate those into individual and community-based risk models. This will help us determine ultimately if increased temperatures contribute to gastric cancers. I want to say, obviously, There's a lot more research that needs to be done on this. Like I said, we're in different phases of these projects, but it requires a huge interdisciplinary team and multiple approaches just to get to this phase. So currently on the team that is just funded by 2 pilot projects, we have 9 different disciplines represented. That includes epidemiologists all the way to data scientists, and it's going to take a lot more before we can actually start to think about the interventions. When we have a complete understanding of the exposures, the disease mechanisms, and the burdens within a community, then we can start to computationally test different interventions. And in this case, we can test interventions specific to Hispanics drinking concentrated arsenic from their groundwater as it relates to the cascading effects of concentrated contaminants from increased air temperatures. So with an idea of exposure pathways, health connections, and scale of the problem, we can start to have really deep conversations about mitigation strategies when it comes to preventing gastric cancers in this scenario. This could be as simple as pollution-specific water treatment devices that we can apply at the individual, the household, or the community levels. But it could be as large as big data, incorporating big data into identifying which communities and which aquifers are at highest risk for concentrating contaminants. And once we have that information of we should be focused on specific areas, then we can make informed decisions about how to prevent the water from being contaminated in the first place, which will save us a lot of money. Ultimately, we aim to use artificial intelligence to link exposures and geospatial information to make those, to address priority high-risk areas, to define optimal mitigation strategies that take into consideration the burden, the cost of the disease, and the longevity of the disease so we can start to use our money most wisely. And ultimately, we want to get to precision medicine, where we can treat a specific group or a specific individual based off of their mechanisms of disease and their specific exposures. So I want to wrap up this gastric cancer case study really quickly just by relating back to we first started looking at exposure factors, and that included concentrated arsenic in groundwater as part of a cascading effect from increased air temperatures. Then we aim to quantify the disease and look at the different mechanisms of gastric cancer. And ultimately, once we have that information, then we can start to develop risk assessments and informed decisions. And this figure is why we're studying gastric cancer in Arizona. The middle line, the blue line, indicates that if nothing changes, we can expect 1.3 million deaths on a global scale resulting from gastric cancers by the year 2040. That is very near term. But we know things are changing. They're not going to stay the same. One example related that our initial results suggest is that arsenic is increasing in groundwater, and that is a risk factor for gastric cancer. So under the worst case scenario, we can expect 2.3 million deaths each year attributed to gastric cancers. This has huge financial implications. Just to treat this number of gastric cancer cases represents $100 billion per year, and that's on just the treatment. That's not associating the other disease burdens that are going to come along with water pollution, because we know arsenic also affects bladder cancer, and we also know there's pathogens in the water, and these are all starting to increase, and so it's goes well beyond this single case study. Gastric cancer is just one activity or one disease that we expect to increase as a result of the cascading effects from increased air temperature. But I end on a positive note, because I think using comprehensive science, we can scale up. We can go from bench scale research to global applications. And we can do that by combining our expertise, by making informed decisions, and by using this model, we can bring together CNRS, we can bring together the experts at U of A, we can share our resources, and we can share our networks, and we can make Arizona the global center of climate and health and air lands research.
Thank you, Mark. Really appreciate it. And I think that was a great example of the kind of integration going from really bench science through environmental health sciences all the way up to understanding and mitigating the effects of climate change. So we're happy to share that example. And as we spend our day talking about challenges faced in arid lands, we also, like Mark just mentioned, want to be turning towards hopeful endeavors and finding solutions, developing interventions, finding ways to solve these problems, and also ways that Arizona can serve as a model for dealing with these issues at a global scale. So to that end, I'm honored to introduce our next guest, Dr. Sylvette Turment, the director of the CNRS Office for the USA in DC, as part of the French National Center for Scientific Research.
Okay, so hello everyone. So I am, as Frank said, I'm Sylvette Turment. I am the director of the CNRS office in DC for US and Mexico. So I will try to show you how the University of Arizona and the Centre National de la Recherche Scientifique, CNRS, can partner to advance global research and solutions for health and climate change. So first, to present the CNRS, this is a large research organization which has a mission to do a basic research for the benefit of society. This is the research institution number 1 in France. 65% of the publications are done in collaboration with foreign laboratories. We are at 33,000 people dedicated to research at CNRS. In fact, CNRS researchers are full-time researchers, and they are working in common labs with people from the university and with people from other research organizations in the different universities all over the country. But we also have such labs abroad. We have 60 international research laboratories, so they are in orange. We have 5 in the US, and we have 1 in the University of Arizona, which is directed by Régis Ferrière. So in these international research labs that we have all over the world, the CNRS people can stay some months or some years, and they are in common labs with people from the host university. So from the slide, we see that CNRS has a large a big network of partners in France, but has also a big network of partners abroad. And to support these international collaborations at the highest level, CNRS is establishing international research centers. So what is an international research center? This is a long-term strategic partnership between 2 institutions, so the CNRS and a university. The first one has been signed with the University of Arizona. This is the IRC France-Arizona Institute for Global Grand Challenges, and it is focused on environmental challenges of global significance. So I would say that an international research center must allow to do research that any one of the 2 institutions could not do alone. The aim of the CNRS is to have 10 to 12 international research centers in the world. So at the moment, we have one in the University of Arizona, one with Chicago, with Sherbrooke in Canada, with Sao Paulo, London, Tokyo, and we will have some others with Toronto, in fact. So at the end, we will have around 10 or 12. And so in each of these international research centers, we are launching PhD programs to prepare for the next generation of collaborators. And so when we will establish a network of these international research centers, you can see that it will give a very a great possibility of collaborations all over the world. So in September 2022, a delegation from the University of Arizona came in Paris at the CNRS headquarters, and the science committee, represented by Régis Ferrière and Gilles Pinet, but also people from the International Advisory Board, supported by CNRS President Antoine Petit, CEO Antoine Petit, and also by the University of Arizona President Robert Robbins, with Senior Vice President Michael Dake, have identified 3 major initiatives for this IRC. The first one is habitability. What makes a world habitable and how to keep that way. The second one is sustainability, integrated food, energy, water solutions at scale. And there is a project on agrivoltaics. So these 2 subjects are already underway. There are already collaborations and also ongoing joint PhD product. So the third priority is climate change and health, responding to unprecedented challenges. So, if I go to the, I think I said everything. So to tackle all these global challenges, of course, interdisciplinarity is essential. CNRS covers all the research domains and is structured in 10 disciplinary divisions that you can see in the circle. So humanities, mathematics, engineering, computer science, earth and astronomy, chemistry, environment and ecology, physics, particle physics, and biology. We have a Directorate for Interdisciplinary Research, which is led by Martina Knoop, who is present today. And the third important thing is that the CNRS is engaged in 6 societal challenges: territories of the future, educational inequalities, energetic transition, and the International Research Center, it's 3 of them, 3 of these strategic interdisciplinary targets: health and the environment, artificial intelligence, and climate change. So you see that we have an outstanding interdisciplinary potential that will allow to tackle global challenges. So this is to show you that projects on climate change and health between U of A and CNRS already exist. The first one, how aridification changes the use of chemicals in agriculture and how this affects health in all communities exposed. And the last one, how aridification changes the risk of infection from soil microbes and how we can prepare for increasing risks. These two projects are supported by the mission for interdisciplinarity at CNRS. And on the map, this is to show you that there is a soil fungus which causes the valley fever, and this disease spreads from Arizona, which is a zone of hyper-endemicity. And this disease, in fact, spreads to Mexico and to South America. And human mobility and climate change are suspected to favor this spread. The third project in the middle, how aridification changes air quality in the school environment and how children's health is impacted, is about to be submitted at the International Belmont Forum. So this is to show you that project between the two institutions already exist, and regular requests or funding are made. So, of course, these issues of health and environment in arid lands are critical to all populations, and we can leverage on CNRS Africa cooperation. So on the Africa map, all the small colored dots correspond to cooperation between Africa and CNRS, and they are supported by CNRS. And in the pink countries, these are countries with projects between CNRS and Africa, and they are supported by a bilateral program. So this is also to show that it represents a very large opportunity of collaborations between Africa and the IRC of the two institutions. So from Arizona, we went to Africa and then to the rest of the drying world. CNRS can leverage major international programs. So the first one is MOPGA, Make Our Planet Great Again. It's a program to host climate and environmental scientists from around the world for long research stays in France. 10 US scientists were awarded of up to 1.5 million euros through this program. And of course, it has created a solid base of France-US collaborations. The Belmont Forum supports international transdisciplinary research, providing knowledge to understand, mitigate, and adapt to global environmental changes. And Future Earth's first major interdisciplinary initiative involved the Sustainable Development Goals, producing the knowledge needed to achieve the 4 goals among the 17 identified by the United Nations: climate, water, terrestrial biodiversity, and marine biodiversity. And the last one, the 30 by 30 initiative, in the framework of the International Research Center, we have initiated a high-level dialogue between leading experts from France and the US on how to achieve protection of 30% of our land and seas by 2030. So to conclude, we are, on both sides, excited to grow the CNRS Arizona international cooperation and global leadership on climate change and health in arid lands. And I thank you for your attention.
Thank you very much, and we're looking forward to see what we can do working between CNRS and the University of Arizona. We're really happy to move into this next session where we can have some discussion. We've had a lot of big ideas and big ambitions that we have for how to address issues with air and water pollution in arid land. So this is our opportunity to have a bit of discussion about it in our panel. Please. Yes.
I think I need the microphone because there are people online.
Yeah.
Sorry. Thank you very much for this very interesting session. I have a couple of questions, but I will start by the last one, which is a question to Gwen Coleman. I mean, you were talking about bringing together the communities from climate science and health and health, and we see that in what we do at CNRS. In fact, the people who are from climate science and those who are coming from health are not the people who are working on health issues under climate change. I mean, it's a different community, which maybe is nourished by these inputs, but it's still a different approach. And so, bringing together these different communities, I find that very difficult, and also it's really in a long-term issue. So how do I mean you talked about that you will have a research coordination and who's working on these good practices and how to bring together communities, but could you give a hint of what's your priority action?
Well,
to do
I
that?
think. Can you hear me? Oh, sorry. Okay. So, I mean, I don't think we are the only institute or institution that appreciates this issue, right? When I look in my own field, I'm an environmental epidemiologist, and I go to meetings and I hear my colleagues, a fraction of them have somebody who understands geoscience or atmospheric engineering or, any engineers that could help them with solutions on their teams. They talk about multidisciplinary work, but it's actually very traditional epidemiology, exposure assessment, and biostatistics. And so, it's not that their work is bad, but could it be better? Could it be more applicable? Could it be more relevant? And of course, working with communities really helps set us up for what's relevant, what's doable, what's going to be taken up by governments or by people. If any of this is related to any kind of behavior change in any way in any of these sectors, you need to have those people at the table. So yes, I believe the Belmont Forum is interested in this. The NSF just put out a Dear Colleague letter asking for their community to think about health. We are talking about this. The Wellcome Trust is thinking about this. I mean, so we're all thinking about it, but I don't think any of us have answers as to how easy this will be. But I do appreciate that it's difficult, but that means even more so we should try to do it and evaluate whether we're effective, right? And see how maybe we can do things together as multiple funding partners in a way that really helps the field to get to the place we want to be.
Great. This was for Nathan. I was just curious about it's kind of the mechanism. You were talking about the heat stress impacting I don't know if it's the expression of the transporters that are affecting the metabolism of the toxins, what have you. The reason I'm asking the question is are there other mitigation strategies besides preventing climate change that would can you do something to impact transporter expression or what have you that don't involve having to solve global climate change?
Yeah, so there's actually multiple mechanisms associated. So the most obvious is a cytokine release, and so the downregulation of the uptake transporters is driven by cytokines, and so that's actually a druggable aspect. There are other types of regulation. One of the transporters that puts compounds into the bile for elimination actually doesn't change its regulation transcriptionally. It actually moves away from the membrane, and so it's an entirely different mechanism. And so every xenobiotic, every toxicant out there has a molecular story, which is is told by this particular enzyme and that particular enzyme. And so there are a lot of compounds where the metabolism and elimination is not changed because the transporters and enzymes aren't affected. But there are some where the transporter or the metabolizing enzyme is affected by one of these multiple mechanisms affected by the stress. And so the story for that compound, whether it's a drug for cardiovascular disease or it's a chemical from the respiratory exposures that you get from being a worker, every compound will have a molecular story. And the complexity of that is enormous, but some of them could be targeted and once they're known. It'll keep me employed for another 50 years, right? And all of my students and their students.
I have a question to Mark. I was really impressed by all the talk today, and I have a specific question about the arsenic, because it's, there's a lot of region. I mean, you mentioned that where we have the geogenic origin of arsenic is naturally occurring, like in Bangladesh or any. And so when these redox sensitive metalloids occur, generally there are, not always, but in some cases there are other redox sensitive metals like manganese. And so I was wondering whether in your specific case in Arizona, do you also detect some like manganese or other redox sensitive metals or metalloids?
We do, yeah. Cadmium, lead, manganese, those are all other naturally occurring contaminants that we're finding in our groundwater. And that's why I focused just on arsenic, but I could have gone off on all the other naturally occurring metals and metalloids in that system. And that's not even to mention the pesticides, the other man-made chemicals that are occurring in the water as well. All of those are being concentrated into the remaining groundwater or the remaining water sources, even on the surface. So for brevity of this presentation, I had to focus just on one, but we know everything else that's in the environment is being concentrated into that water. And if that's the person's sole source of drinking water, they're going to be exposed to that through consumption. And only 5% of rural communities who rely on groundwater treat their water before consumption. And 99% of the wells never test their water in the first place. So it's just this ginormous hurdle that we're going to have to get over. The individuals that we've worked with in the past who have who we've measured their groundwater and shown contaminants, and then we've given them an intervention, don't use it because it's naturally occurring water, and that's safer than whatever treated water that we're trying to sell to them, basically, is what they have come back. So there's psychological and there's social behavioral hurdles, and it's not something as simple as here's bottled water or here's a treatment system to fix your problem. So it's growing beyond the science and into the psychology. Correct. Yep.
I would just add that there is also manganese pollution issues in Arizona and across the border in Mexico. So there's opportunities to explore this further.
And there's certainly discussion about cocktail effects and stuff like that. I mean, we can discuss about that tomorrow. It will take us more time. I had a question to Nathan about the heat stress. Do people, I mean, we talk a lot about adaptation also to climate change. I mean, can people adapt to that? And I mean, if you're a worker working under these extreme conditions for a long time, will you get used to that? Can you train to be exposed to heat, and will that have an effect? And we talk about also adaptation in the long run to effects of climate change. Is there a chance that we get adapted to a certain extent?
So simply speaking from sort of a global perspective, we do know that there are adaptations for the environment that you live in. People who live close to the equator look different than people where my ancestors come from. So yes, there are adaptations. But at the same time, right, there are, it's a little bit probably irresponsible to say that this could be a contributing factor, but chronic kidney disease of unknown origin, it's in places that are warm, younger men engaged in agricultural work, and if the heat increases their exposure and the resulting toxicity, it's certainly because they didn't adapt. And so there are adaptations, but it's a complex consideration to have.
Longer term and longer cycles.
Wow, I don't know it's a really hard answer to come up with, but
So I think of it sort of like an evolutionary kind of thing, right? There's altitude acclimation that you can, you can prepare yourself by, being at higher altitudes and getting accustomed to it. But then there are peoples who, evolutionarily have changed because they survive in those climates, right? And we don't know all the mechanisms of how all of that happen. So in the face of that, that's too long to wait, right? So these other kinds of interventions, so to speak, are so important for workers, right, who have these extreme events that are occurring, or these changes in their day-to-day work environment that they weren't preparing for. And so what is it that we offer them? How do we change the workday? How do we provide the assistance that they need, the breaks, the hydration, the protective equipment, the shade, building construction sites in a different way so that, you don't have this relentless heat, coming down on your head. If you think about it, there's hundreds of small ways to do some of this. And that the question is how to pull it together so that it makes sense for the environmental change that's occurring in a hyperlocal area so that you can bring the best practices. The other thing is that as these things develop, will people use them? Will they make a difference? Will they adopt them? And the cooling center issue is one that I know in Arizona, the CDC has funded the local health department with people at universities to look at cooling centers. Who uses them? How productive are they? Are they efficient? Are they located in the right parts of the community? Do people really want to go to a cooling center, or do they want to have cooling adaptation in their own home or their own neighborhood? So there's all these different questions that are still very relevant, even as evolution and biology will change over decades or hundreds of years, no matter what our environment changes to.
There's clearly a short term and a mean term. Right. There's clearly a short term, a mean term, and certainly maybe a long term evolution. This is why I said adaptation and maybe training or getting used to something, which is more in the shorter time. And I completely agree that we should think about these short term things also, but maybe we will also. Well, I don't know. Maybe we can train to being exposed to higher temperatures.
A couple of questions. I want to respond to this adaptive stress response. I just actually in my lab completed a hot yoga study. And I'm not sure I've ever seen an intervention that changed more things in a positive manner. Now, again, is it the yoga or is it being at 105 degrees? But I think your point is well taken. This was simply 6 weeks. What the body can do in 6 weeks, and its ability to adapt, both immunologically, its use of oxygen, its use of many so the hormesis response has been around forever, and we know if we get on top of that bell-shaped curve, we increase our health. If we go over the bell-shaped curve, it gets very bad. So I think you're making a really important and interesting response. I guess I had a question to Mark, and I'm sorry, I don't mean to, but how do you know? So I study gene-diet interactions in different ancestry populations. And so how do you know when you see increased GI cancer in a population, that's being driven by an environmental or, and I guess diet is an environmental. It's I mean, again, we throw all of our money towards gene-diet interactions, but how does one tease apart what's driving GI cancer in a Hispanic or a Native American population?
Yeah, this is actually probably a question more appropriate for Gwen, being an environmental epidemiologist, because we very rarely can get to the point where we say we have definitive proof that something is causing a health outcome. So in this case, I presented one slide with 3 different layers, with the exposure, the disease mechanism, and the disease burden. That's actually another term that's been thrown around for a little bit, for a few years, of triangulation of collaboration or cooperation, right? And so we need multiple studies designed in multiple ways. And once they start to overlap with the same conclusion, then we can start to get to that point of concluding one, say, gastric cancer stems from either increased temperature or arsenic. Gwen, do you want to build off of that?
Well, I think I want to point to Frank's work, right? Using a One Health model where you can, create scenarios in the laboratory. And I'm sorry, I don't know you well enough to know if that's the kind of thing you do. But
I
if
just
you
work with humans.
Well, okay. So, but using the animal literature where, you can have particular strains, different genetic backgrounds, creating these interactions, and then understanding trends, looking at populations in different parts of the world and building that evidence base, I think helps you bring it all together to tease out those pieces. I think epidemiologic research will never, ever tell you that it's exactly that, because there's so many factors to consider, and we don't have perfect measures to be able to do that. And it's probably not just gene and diet. It's probably gene, diet, and then 5 other factors that is very difficult to consider all at the same time.
Absolutely.
But very worthy work for sure.
And there are a lot of excellent animal studies along that line, including many studies with fish. Fish, teleost, bony fish, share 70% of their genome with humans. 82% of human genetic diseases are shared with fish. So you can get at some of these genomic or gene by environment interaction studies using fish with high throughput kinds of approaches. I think we had a question. Okay. While we're waiting for the next question from the audience, I actually have one that might be mostly. Nathan, do you want to make a
I
comment?
actually have a question for Sylvette. Is
Go
that
ahead.
Okay? So NIH funds a particular style of project that's sort of mechanistic heavy. What kind of research projects do you foresee being most valued by CNRS in conjunction with the work done at Arizona, trying to establish a sort of an international arid lands consortium? What would be most attractive to CNRS?
I think my colleagues can perhaps respond. I think it will be also we will discuss about that tomorrow. So see what are the forces on both sides and what we can do together. Perhaps, I don't know whether Anne-Marie and Sylvie have already some ideas today, but that it will be the discussion of tomorrow, in fact.
And I think it's also about the multitude of projects that, I think what I see from today is there are different approaches of University of Arizona and CNRS. CNRS is maybe in a certain sense a bit more fundamental, and your projects are a bit more pragmatic or applied. And I think the good thing would be, we started to have some common projects, and I think the idea, our main idea, is not to have 1 or 2 projects, but to have a sort of a panorama or a mosaic of different projects will come together and look on different aspects, because the question is so large. There will not be one axis or one project. I think there are 3 axes which have been discussed before. And I think if we can build around these access, but we'll never be a sort of have a complete approach. I mean, we'll just have some contributions, and I think our idea is to look on how we can build a couple of approaches so that we can be the most efficient. But well, that's a very vague answer to a very concrete question.
Yeah, I like what you said, because when we first started this, it often felt like we were trying to boil an ocean. You know, how do you get a handle on this? And the only way is just dig in and start with some projects. And, you know, what we're doing may not be the perfect project or may not be the most impactful project, but it's relevant at some degree. So I like what you said about having this portfolio. Just a quick observation of something that climate change in Arizona, how it affects people. Back during the pandemic, and it was very hot in the summertime, I would have to visit to talk to researchers at the Cancer Center. And you'd get screened at the Cancer Center by doing temperature because, you know, you might have COVID, you couldn't come into the Cancer Center, all of this. I'd routinely go there and my temperature would be 104. You know, just from being out, driving the car, parking the car, walking. So they would then put you in front of this giant refrigerator-sized air conditioner and blow cold air on you. And so there'd be a line, and it was like being in the, you know, sort of equivalent to a recipe. When your temperature got down, then they'd let you in. So here we are outside a line of like 10 people waiting to cool down in front of these, you know, ice machines. And I just think, wow, what in the world? Any event, my question, maybe to Mark, maybe to Frank, maybe to Gwen, we didn't talk a lot about microbes in pollution. That was one thing we didn't really cover. And I'm just sort of interested, the overview is with heat, drought, are we changing basically the diversity, the dominance, the pathogenicity, the whatever of microbes, and what are you seeing in your work that we should be worried about?
I'll do a quick response. It's a great question, and actually when Gwen said there's probably 6 things we need to consider, not just gene, environment, blah, blah, blah. One of those is the microbial community is a very important one. We actually just finished a study that's not published yet that's using the fish model to look at how certain kinds of pollutants impact the gut microbiome and what impacts that might have on health. And many people are doing these kinds of studies. And then there's the whole, if you go to the Superfund kind of thing that Gwen was talking about, the microbial community is critically important to breaking down pollutants in the environment. And there's a lot of really interesting research happening there. So we need a whole day to talk about your question, but there's a lot to it, and it's a super important part of the whole question in climate change and environment and health.
So on a specific pathogen side, we know Vibrio cholera is actually spreading to more places around the world as the water temperature increases as well. And so the World Health Organization just put out a concern or a cause for concern about Vibrio, because it is popping up in new geographies that it hasn't in the past, and this is leading to a lot of waterborne diseases. So that's also a similar species, Vibrio, and Vibrio perihemolyticus is a shellfish pathogen, and it is the same thing, that it's showing up in new oyster growing environments that it hasn't in the past. So the implications are for human health and for agriculture as well, and that's just one microorganism that we're starting to see move as temperatures increase. But we also know with the concentrating contaminants in water, we're also see concentrating of pathogens in those same waters. So the communities will change.
So if I were to channel my colleagues at the National Institute of Allergy and Infectious Disease, they'd say that climate will impact every single one of the different types of microbes, and there's already data and review papers that have come out in the last couple of years that sort of lay that out actually quite well, and you can see the temporal and geographic distribution, which populations are most at risk, et cetera, et cetera. And I actually talked to a colleague just this week, and a couple of things that he reminded me of were that as temperature increases, the antimicrobial resistance goes up, and so that's part of the story, and that's about how to treat these illnesses when they happen, what vaccines are needed, for future prediction of how these diseases are going to move around and be exacerbated by different climate factors. And then whether the vaccines that we have for these will be effective under those new circumstances, and then how those vaccines could actually be delivered, in the new climate impacted environments around the world, supply chain issues, cold chain issues, all those different pieces. So you can think of it, it's again, another giant thing to think about. I spoke at the American Society of Microbiology this year at their annual Microbes 2023 meeting. That society has put out quite a number of policy documents around where this area is headed related to climate. And it's not just health. They're interested in, microbes for agriculture, microbes for economic development, microbes in every part of society. And so I just encourage you to look at their website. There's a lot of interesting information that they've put together.
So while we're waiting for the next question from the audience, as a researcher and as someone who also runs a research program, I'm always concerned about where do we get the funding for what we want to do. And I know we'll be discussing a lot of this tomorrow in our meetings with CNRS, but since we have you here, Gwen, from the NIH, I'm wondering if you have any insights into what are the best mechanisms for international collaborations like this, in this case between France and the University of Arizona. I know that NIH sometimes has country-specific binational funding mechanisms, like with Brazil or in the past with China. But what do you suggest for, in this case, for France, Arizona, arid climate change, pollution kinds of things?
So one of the things I learned today was all about your agency. Wasn't really that familiar with the CSR space, and so found it really fascinating to hear about what you have and what you bring to the table. So I'd personally love to learn more and would welcome an opportunity to talk with you. Seemingly good partnership between powerhouse biomedical research funders is a good way to go. There's a climate and health funders sort of community growing, and the Rockefeller Foundation and Wellcome Trust are really interested in seeing that happen. And they had a convening in April, but there was nobody from your organization. There were other people from smaller groups and nonprofits that were funders, mostly on the climate mitigation side, that were there from France. So I'll give you some information and see if you are interested in joining that. Again, too, I'm things like the Belmont Forum is just a good place for our scientists to be part. They have a lot of community building and capacity building, matchmaking, collaborative kinds of things that are happening, and so that's a place where anybody from Arizona, anybody from your research organizations, I think, can become part of that. And then they bring together funding sources from a lot of different places for different calls that are in this space. And then, you can then pick the ones that are most relevant to the work that you're doing here. So anyway, those are just some ideas.
We will have a project which is the project of Michael, which is about to be submitted at the Belmont Forum. Mm-hmm. So perhaps you can talk about this project.
Well, it's basically about what you showed before, trying to have a network of sensors at different level of quality of the data, and how artificial intelligence can lower the cost of the surveillance, so increase the space of what is going to be surveyed for this, at a given cost for society, and basically show the impact on school was one of the example. It's also including some Mexican colleagues from the desert across the border, so University of Sonora. So yeah, and I'm CNRS full-time at University of Arizona, so very much looking forward.
Thank you very much. It's really been a pleasure for me to serve as your moderator, and it's great to have so many experts from around the world here. I want to thank our panel today for having this exchange of ideas. And I'd like to invite everyone in the room up to our rooftop DC Center for Outreach and Collaboration, where we're going to have a reception. So once again, thank you for your attendance today.